Hi there, thanks for joining us. This is a Q&A edition of Space Nuts. My name is Andrew Dunkley. So good to have your company. Coming up, we are going to answer a question from Christian about the origins of life. We talked about that sort of in the last episode. Well, there's a question on the table from the audience. Rennie wants to know about the pitfalls of traveling to Mars. Aside from being next to Elon Musk, there are other things to consider. Lawrence is asking how we judge distances in space, and Lee wants to know about whether or not there's a possibility in the future of James Webb Space Telescopes 2 and 3. That's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And in the stead of Professor Fred Watson, we are again joined by Jonti Horner, Professor of Astrophysics. Hi, Jonti.
Hey, how are you going?
I am well. Good to see you again. We have got plenty of questions to answer. They're all text questions today. I didn't get the audio questions in time, but we'll save them up for future episodes. And we might as well get straight into it, shall we?
Yeah.
All right. Happy New Year. I've been listening to your podcast regularly for over 5 years now. Well, some people go to prison. You did that. And it's been a source of inspiration for me. In fact, it partly motivated the work I currently do, which is why I wanted to share some exciting news with you. We've finally published our findings in the Proceedings of the National Academy of Sciences. Our study explores the origins of life and argues for its significant implications, not only for Earth, but for other planetary bodies across the universe. I'd be thrilled to hear your thoughts on it. Fred's mentioned my colleague Juan Manuel Garcia Ruiz's earlier work a few times on the podcast. Recently, we embarked on an exciting new project collaborating with the ExoMars science team at the European Space Agency. It's an incredibly stimulating area of research, and I hope it piques your interest. And that comes from Christian, and forgive me if I mispronounce your surname, Christian, Gene Wayne. I hope I'm close, but I'm kind of gobsmacked that listening to us kind of partially inspired this work. I never thought I would see the day where something we did could lead to something like that. Not directly, but obviously, a few things we've said has got somebody thinking, which is what we hope to achieve.
Well, absolutely. It's fabulous. And congratulations to yourself and Fred by proxy for motivating and inspiring. I think that's fabulous. And that's one of the real values of this kind of work. Before we dive into the awesome paper here, one of the important things with podcasts like this, with TV shows, with astronomy outreach in general, or astrobiology outreach, is you don't know where it's going to end, but people get inspired. And I wouldn't be here if it wasn't for Patrick Moore doing The Sky at Night back when I was a kid.
Yeah.
And it's fabulous to see that impact, and that, genuinely huge kudos to you and Fred for having such a fabulous podcast and clearly going out and inspiring people. So that's fabulous. And it's lovely to hear this story. Now, the article itself is on PNAS, which is, as it says, the Proceedings of the National Academy of Sciences. The challenge with that, and certainly I'd quite happily recommend people have a look at the paper, but one of the challenges when you publish in a journal as prestigious as that is that papers have to be very short and concise, which sometimes makes them harder to dive into. And I think the authors here have done a very good job of dealing with that, but it is a slightly challenging read if you're not banging the discipline. But I've had to read through it, and it's a fabulous piece of work and really, really interesting. So what they've done is building on a really fabulous history called the Miller-Urey experiments. This was the idea that people are fascinated with how life got started. And way back in time, there was this experiment done which essentially attempted to bottle the atmosphere that the early Earth had and then pass electricity through it, essentially simulating lightning and UV exposure on that early atmosphere. And it showed that you could get some kind of prebiotic chemicals forming from a very simple atmosphere in those kind of conditions. So it became very much a touchstone of early astrobiology. went out of fashion for a while because people argued that the early Earth wasn't like that. But recent studies have shown that those kind of conditions probably were important. This work then kind of builds on that. They've done a similar experiment with a much more modern and much more nuanced setup and looked at the results in a lot more detail than could have been done all that time ago. And what's really interesting is, again, with a really simple setup, they get quite a complex stew of different ingredients forming. You get this layer of stuff floating on top of the water, essentially. But they've dug into that, and what they found is that in that watery layer, there is this, what they almost describe as protocells, these globules that are quite small, that are spheres with a membrane that are possibly hollow inside, that could be, prebiotic chemical factories, essentially, the places where chemistry can happen in really interesting ways. That's really interesting, and they're talking about these biomorphic protocells. Now, there's positives and negatives to this. So one of the negatives from this research is that when people look for evidence of the earliest life on Earth, or in future when they're looking for evidence of the earliest life on Mars, one of the things they'd look for are these kind of protocells, things that are a precursor to the cells of life we know. And the argument has always been that these are separate to the formation of the compounds, and therefore they could be seen as a discrete bit of evidence of the start of the origin of life. And what this work is saying is that these can actually be something that forms concomitantly, that's the phrase they use in the title, forms at the same time as those prebiotic chemicals. So finding these globules is not necessarily evidence that life has begun, but rather that the conditions needed for life were there. So it's maybe saying when you look back at the historical record, this is not a definitive sign of life necessarily, but may instead be a sign of the conditions for life to then develop in the future. So that's a little bit sad. But on the flip side, what it's showing is that these conditions where you can start to get the conditions needed for life to start could be quite widely distributed, because this was fairly simple. These are the kind of conditions you could get on planets across the cosmos with similar conditions to the Earth. So the other outcome from this is that this thing that sets the scene for the emergence of life could be more common than people think, that places where you've got oceans and atmospheres like this could get these protocells, these globules, that act as accelerators, incubators for advanced chemistry. That could be more common through the cosmos, and therefore the scope for finding life out there could be greater than we thought. So it's a really interesting piece of work, and I think the way that they balance the positive and the negative outcomes is really quite cool. Now, it is quite a complex paper to read because of the nature of having to be condensed for this very prestigious journal. Yeah. But the results are fabulous, and if you do get onto it and have a look at it, the entire presentation is available online, and some of the figures are beautiful. Some of the images that they've got showing the globules and the microscopic structures they've got are really beautiful. And it's the kind of thing that you almost wish that back when Urey and Miller were doing their experiment originally, we could have had that same quality of imagery and results to go back and look at. So I think it's an absolutely fabulous piece of work. And I'm really interested to see where it goes next and how people react and interact with it. In other words, what research does it spawn next? Are we actually going to get to the point where we get a distinct idea of where life began? And also, what the difference between life and not life is? There's still not really a hard and fast definition of when something is life and when it isn't. Yeah, which always makes my head hurt. I'm an astronomer, I'm not a biologist. And I remember at one of the early astrobiology conferences I went to, talking about life, and somebody mentioned viruses. And all the biologists said, oh no, viruses aren't alive. And that's totally contrary to my understanding as a layperson, as a generalist, as an astronomer. I was gobsmacked. But apparently, by most biological definitions, a virus is not alive. And I don't understand how that works. Now, it's, again, back to that old carrot about you've actually got a spectrum from definitely not life to definitely is life. And we have to put the dividing line somewhere. But I don't know that there's a consensus on that yet. And that kind of feeds into this as well, in that this kind of work might help people figure out that process and therefore help them put a line on this is where we consider it to be alive versus not, essentially. So yeah, fabulous work. And even better, I guess, even more inspirational given the links to the podcast in the past. I think that's fabulous.
Yeah, I'm chuffed. Fred does most of the talking. But I have always argued that the recipe for life exists everywhere. You've just got to have it, all put together properly and have the right oven to make it happen. And I've always believed that when you look at how life flourishes on Earth, how a weed can find the slightest crack and grow.
Yes.
I mean, it stands to reason that life could flourish anywhere in the universe if the conditions are right, because we have learned that the building blocks of life, all the bits and bobs that we need to establish life, exist. They're flying around the universe as we speak. So it's not a giant leap to consider that, if it hits something that's exactly right, boom, you've got life somewhere else. I don't doubt it exists now. It might not be life as we know it. And as you said, what is life anyway? The same question that the great George Harrison asked. And there is no real definition of what constitutes life. How do you, when I was a kid, I had a pet rock. It could have been alive. You don't, where do you draw the line?
Especially real estate out there as well. So it's not like you're limited in space. We've got an incredible volume of space, an incredible depth of time. And what's always struck me as interesting is the division between those who believe that life won't be out there and those who will. And I saw this when I'm one of the members of the committee of the Astrobiology Society of Great Britain, even though I left the country 15 years ago now. But there's an active astrobiology community there, and I first started going to conferences with them more than 20 years ago now. And astrobiology conferences are wonderful things because they're so multidisciplinary. So you've got learning in areas that you wouldn't normally encounter where you learn something new. You've also got kind of sociological learning of the way that different disciplines present. Different disciplines have different color schemes, which I'd never thought of. I've been to talks by geologists that were pink text on a pale blue background, which made my eyes bleed. But, you get these differences there. But one of the things that struck me early on was that the people involved in astrobiology from the biology side were nearly all very young researchers, really passionate and excited. But because the senior biologists were convinced that life was impossible and they thought that the search for life elsewhere was a fool's errand, that you just couldn't have life. Now, if you think that the Earth is the only place in the universe with life, which, we've got a sample of one, so that is still possible, then you have to assume that life is so incredibly impossible that we're a fluke. If you make life even slightly more probable than that, even if it is not impossible, but just vanishingly improbable, because there is so much real estate, because there are so many planets around so many stars in so many galaxies, even if life is vanishingly improbable, it must be everywhere. It just might not be close enough for us to find. And that divide is really stark, and it's a philosophical one, because we have no evidence either way, and it becomes almost a belief structure. People believe that we must be alone, or people are convinced that we're not. And the only way we'll find out is by looking and by doing this kind of work. Yeah. And I would love to think that within our lifetimes, we'll know the answer.
One can only hope, yes. If you would like to find that paper, it's at pnas.org, pnas.org. Oh, that didn't sound good. It's a long title, but it is really
concomitant formation of protocells and prebiotic compounds under a plausible early Earth atmosphere.
There you are. And it's not a long read, but it is, it can make your brain hurt. But most scientific papers tend to do that. But and thanks, Christian, for letting us know and telling us that we had a tiny part to play in the development of your work. That really excites me, and I'll make sure Fred's aware, and he might want to talk about that when he gets back. To our next question, this one comes from, who is it? It's from Rennie, who is in sunny West Hills, California. Rennie tends to ask very short, sharp questions. On a mission to Mars, would a spaceship traverse through the asteroid belt, or would it travel above or below the belt?
Yes, really good question. Now, the asteroid belt, as everybody imagines it, is between the orbits of Mars and Jupiter. So when we're going to Mars, we're still closer to the sun than the asteroid belt is. So you're not really going to be traversing the belt anyway. However, Mars is such a tiny, puny planet with fairly weak gravity, and sorry, Mars, but it's true, that the inner edge of the asteroid belt basically almost overlaps with Mars's orbit, and asteroids do cross Mars's orbit all the time. Mars, therefore, gets hit more often than we do. Fortunately, space is really, really, really big. And there's a experiment you can do that demonstrates this. So if you've watched great movies like Star Wars, you've got asteroid belts in there as a refuge for the brave, heroic enemies of society. And, being chased by the baddies, they fly into the asteroid belt and they have to dodge and weave to get through. And of course, the baddies fail terribly, crash into things, and we cheer because at heart we're all horrible individuals. But that's what happens. So the kind of cultural take from that is that we imagine asteroid belts as being incredibly densely packed with material. Now, if the asteroid belt was like that, you could go out tonight or any night of the year and look up, and the plane of the solar system would have a band quite broad of the sky from horizon to horizon where you see no stars, where you cannot see Jupiter, when you cannot see Saturn, because there's an asteroid in the way, because every line of sight would hit an asteroid. And that would be glowing greyish because it'd be reflecting sunlight back to us. That'd be how the sky looks. The reality is that you don't see the asteroid belt. You need a telescope or binoculars to see individual asteroids. But to have an asteroid pass in front of a star and block its light, to have an occultation, is a sufficiently unusual event that astronomers will travel across the world to set up in the shadow of the asteroid to get data that tells you how big it is, what its shape is, by the shape of that shadow as it moves across the Earth. What that tells you is that space is mostly empty. The fact that it is so rare that one of these asteroids lines up with a star is telling you that essentially you're going to be fairly safe traveling through the asteroid belt. When you talk about there being more than 1 million objects bigger than a kilometer across, you think space must be packed. But in actuality, that belt is so sparsely populated these days that if you were ever to be stood on the surface of an asteroid and you weren't having to worry about how you get home or what you're going to breathe, if you're stood on the surface of that asteroid, very few other asteroids would be near enough to see with your naked eye. Space is that big. The way that you can evidence that, I guess, is the fact we've sent all these missions to the outer planets and not one has come a cropper. But also, when those missions want to visit an asteroid for a bit of added value, they've got to be very careful in picking their trajectory to get near enough to see something, because space is pretty big. So in terms of this question, for a mission to Mars, there is debris in the inner solar system that you'd want to be aware of, but you can basically just pick your path and go. The odds of you intersecting an asteroid are pretty much non-existent. Very, very small. Smaller debris maybe, but the bigger you get, the less stuff there is. Even going to the outer solar system, you just go through. You don't need to go above or below, which is fortunate because the orbits of the asteroids are quite puffed up. You'll get up to 30 or even 45 degree tilts before the asteroid belt starts to wane. And so that means you'd have to go very, very high to get up and then get back down again. A lot easier to go straight through.
Yeah. And as you said, nothing's hit one yet that we've sent out there. So, there's plenty of room to move through. And as you said, space is big. You might think it's a long way down the street to the chemist, to quote a famous book, but yes, space is huge. Thanks, Rennie. Great to hear from you. This is Space Nuts with Andrew Dunkley and Jonti Horner. Time to take a short break to tell you about our sponsor, NordVPN, and they've got a great New Year deal for you, which I'll get to soon. Now, if you're someone who uses public Wi-Fi, then you could be exposed to hackers. And I'm talking about places like cafes, airports, hotels, shopping malls, anywhere that Wi-Fi exists for open use, basically. And let's be realistic, there aren't many places that don't offer it these days. Now, you might not be aware of this, but there are two ways hackers work. They can hack into your device directly, or they can intercept your Wi-Fi data, which could include your passwords and usernames. And once they get that, all bets are off. So what can you do to ensure your safety? Simple. Put up a wall known as a virtual private network, or VPN. This is software that makes you untraceable and therefore unhackable, and there's none better than NordVPN. As a Space Nuts listener, we have a special New Year offer available to you. Just go to nordvpn.com/spacenuts. That's nordvpn.com/spacenuts and click on Get the Deal and check out what's on offer through their monthly, yearly or 2-year plans. And the longer you sign up, the lower the overall price, plus an extra 4 months free and, of course, their 30-day money-back guarantee. And don't forget all their other amazing tools like cloud storage, threat protection, anti-malware. My favourite is the password manager, makes life so much easier. All available depending on which plan you choose. It's inexpensive, simple to set up, and you can use it on 10 devices through most operating systems, which is very impressive. Check it out today at nordvpn.com/spacenuts. That's nordvpn.com/spacenuts and click on Get the Deal. You won't be disappointed. Now, back to the show.
0G, and I feel fine.
Space Nuts.
Well, it's not Professor Fred Watson at the moment. It's Professor Jonti Horner. Fred's away, and that means the mice can play, Jonti. Let's go to our next question. Hiya, chaps. Lawrence from London, England here. I have a question about how we map the night sky and judge distances accurately. Specifically, how can we make any kind of objective claim regarding the distance and positions of particular stars or planets when we know effects like gravitational lensing can actively disconnect what we see with what is actually out there? It seems that without any sort of unaffected control against which we make these judgments, it's not all some giant, if not educated, guessing game. Apologies if I've missed something incredibly obvious here. Love the pod, listen to it every day and to and from work. And congratulations, Fred, on the big step in your career. You're an inspiration to all. Cheers, chaps, all the best. That's another one I'll have to send to Fred. Yes, measuring things in space. How do we get it right? How do we compensate for gravitational lensing? I think we've had similar questions in the past, but it's always good to revisit these things.
Absolutely, and it's a good question. And we actually cover a lot of this when we teach astronomy. So I've taught this, I've gone through it. And it is true that the distances you get are not perfectly precise. So we can't say that an object 4 million light years away is exactly 4 million. There'll be an uncertainty with that. But the way that we've got the distances worked out is a series of different rungs on a ladder. That's how it's often described, the distance ladder. And there are different techniques we can use that find objects that are more easy to spot but are rarer. So within our solar system, it took a long time, but people got the distances worked out. There were clever experiments that went on all the way back to the 1600s and even earlier, trying to estimate the scale of the solar system. Famously, Ole Rømer, back in the 1670s, I believe it was, did some cool experiments trying to measure the speed of light, looking at the eclipses of the moons of Jupiter. And in order to measure the speed of light, he had to have an implicit understanding of the scale of the universe, or at least a scale locally in the solar system, in order to make that happen. And that scale, the distance of the planets from the sun, had got relatively well established by then, thanks to clever observations using trigonometry and using little bits of things like trigonometric parallax. Now, parallax is going to become quite important. So within the solar system, once you've got your ruler worked out, if you know the orbital period of an object, you know its semi-major axis, which is the scale of its orbit. We also, by observing from different locations, can get quite a good immediate measurement of the distance, even to things we've only just discovered. If you observe from two different sides of the planet, you'll see the thing move a little bit against the background stars, and that gives you a distance. Now, that technique, that idea of parallax, comes in really important to measure the distance to the nearest stars. And this is what people were doing by the early 1800s. You've got people like Johann Friedrich Bessel were doing this way before the days of photographic observing, should I say. This is all optical with the eye. But they were taking very precise measurements of stars against the background stars using the biggest telescopes of the day. And they use this technique called trigonometric parallax. Now, if you're driving while listening to the podcast, don't do this. But if you're sat somewhere safe, you can do this as an experiment and actually see how it works. So if you put your finger up in front of your face and close your right eye and look where your finger is against the background, then open your right eye and close the left. You'll see your finger move against the background.
Yep.
The closer your finger is to your face, the bigger the movement. So that's trigonometric parallax, and it's part of how our brains help us do things like catch a ball that's thrown to us. We get a sense of depth perception. Now, what I want you to imagine is that without killing you or causing you pain, I'm able to separate your eyes, and instead of them being a couple of inches apart, make them 300 million kilometers apart. So I'm putting them on one side of the Earth's orbit around the sun and then the other. That gives you a much bigger baseline, and that baseline is enough that nearby stars, when you look at them through a telescope, will appear to move against the background stars in just the same way that your finger does when you look from the left eye to the right eye. So that gives us a way to measure the distance to those stars so long as we know the distance that the Earth has moved. That's the distance of the Earth from the sun. So if we know the size of the baseline, we know the angle that the star's moving through, fairly simple trigonometry allows you to calculate the distance. And that gives us the distance to the nearest stars. And the better your telescope, the better your facility, the more accurately you can measure that, which is why the Gaia mission at the minute is so incredible. The Gaia mission is this spacecraft floating around out there in space with an incredibly precise camera that is, among many other things, measuring the parallax and the proper motion of about 2 billion with a B, 2 billion stars. That's, depending on the number you estimate, 0.5% to 1% of all stars in our galaxy will be able to have their distance measured by this spacecraft. But eventually things get so far away that you can't use parallax anymore. They just move too little for you to measure it. How then do you get the distance to the next object? Well, you go back to the early 1900s and you had a great astronomer, I think it was Henrietta Leavitt, who did this fabulous, fabulous work as one of the calculators, one of the astronomers at a great American observatory. And she was looking at photographic plates of the Large Magellanic Cloud, which is one of our satellite galaxies, and studying them. And what she realized was that there was a group of variable stars, which we call the Cepheid variables after Delta Cephei, which is the brightest one in the sky, that were all varying periodically. They were getting brighter and fainter, but the stars that were the same brightness that were varying this way also varied with the same period. Now, because all these stars were in the same galaxy a long way away, they were essentially at the same distance. The size of that galaxy compared to its distance is quite small. So all the stars she was studying in that field of view, in that galaxy, were effectively the same distance. So the stars that looked fainter actually were fainter, and the stars that looked brighter actually were intrinsically brighter. And what she found was that there was a relationship between the period of these oscillations and the brightness, which is brilliant. What that means is if you see a star oscillating in this way and you measure its period, you know intrinsically how bright it is, and you know how bright it is in the sky, so that allows you to work out its distance as an equation we can use, which allows you to compare the true brightness and the observed brightness. So that gives you an independent measure of distance that tells you which of these stars are closer or further away across the sky. But you need to calibrate that. You can say that one star is closer than another, but until you know the distance of one of the stars, that's not really useful. But fortunately, the very closest of these Cepheid variable stars are close enough to also measure the distance with parallax. So that gives you a way to quantify the scale. Now, these are quite bright stars, so you can even see them in nearby galaxies. So that gives you another rung on the distance ladder. And you can see these stars, you can spot them, you can measure their variability, which tells you how luminous they are, how intrinsically bright they are. And you can measure how bright they appear and use that to get the distance. And that gets you out a bit further. But then again, they get too faint, you can't see them. But there are some types of supernova explosion that it turns out are very, very regular in their peak luminosity, how much light they give off. So if you see a supernova behave in a certain way, can identify it's one of these kind of supernovae, then that tells you, you know, exactly how luminous it got. And once again, you can measure the brightness as we see it, put the two together to get the distance. With those, we can use the Cepheid variables to set the standard, these standard candles. You can get the distance of those supernovae, and that gives you your distance scale. So there are other ladders, other rungs on this ladder, but that's the essential way it works. Now, it's not perfect. There are uncertainties that accumulate as you go further and further away. So the more distant something is from us, the larger the uncertainty on its distance will be. So for objects in the solar system, we know the distances with incredible accuracy nowadays, particularly for the objects we've studied really well. The nearest stars, again, we know that very, very accurately, but not as precisely as we know the distance to the objects in the solar system. And the further you go, the bigger the uncertainty, the bigger the error gets on the measurement compared to the measurement itself. Now, all of these things like gravitational lensing and stuff like that interfere for some objects in some locations, but they're not the end of the world because they're a small subset of the objects and they're a small effect on the total of it. So if you've got, and this is getting a bit further from my personal area of expertise, but if you've got a distant galaxy that is lensed by a foreground object, the distance along the different light paths is still going to be very similar to it coming direct. You're only deviating by a couple of degrees off that line and then getting bent back. So even if that light's had to travel a little bit further, the uncertainty is still within all the other uncertainties there. So that's a part of the story as well. And we can observe these things. Now, one of the nice things is for some of the really extremely distant things that are lensed, that lensing gives us a brighter image than we would get if the thing in the foreground wasn't there, which has allowed people to observe these supernova in them to help give an independent confirmation of their extreme distances. You've also had a couple of quirky occasions, I believe, where you've got these fragmented lensed images, these beautiful things you see in some of the astrophotos from things like Hubble, where you've got a distant galaxy with a lens in the foreground and you've got multiple images of the same galaxy. And I believe, that I stand to be corrected on this, that there has been a case at least once where a supernova has been seen in the different fragments of the lens coming at slightly different times because the light paths are different lengths. So we can even see the differences in the distance for the different images because of the asymmetry in the lens. The fact that it's not perfectly centered, essentially. So there's a lot we can dig into there. And if you want to know more about it, searching, the kind of galactic distance scale, the distance ladder, looking up Cepheid variables and the story of the incredible scientists in the early 1900s, the women who worked there and did this remarkable science is well worth looking into as well. You've got people like Henrietta Leavitt, Annie Jump Cannon, who did similar work at the same institute at the time. These kind of overlooked heroes of astronomy that did absolutely astonishing work and led to this knowledge that we have now.
Wow. There you go, Lawrence. I bet you didn't expect that answer, but you've got plenty to work with. So off you go, do your homework and get back to us when you've got another follow-up question. But it's a great explanation and there's a lot more to it than meets the eye. Boom, boom.
Roger, you're loud and clear here also.
Space Nuts.
One final question, and this one comes from Lee. I'm listening to the episode discussing the 9-to-1 subscription rate for the James Webb Space Telescope's time. I understand that JWST costs a few dollars, but surely most of the cost was in tooling, contracting, etc. Wouldn't NASA have contract options to build additional systems, such as in the event of a launch failure? Since the tooling and such is already made and the science value is so high, would they ever consider building James Webb Space Telescopes 2 and 3? Just seems logical to buy in bulk. Keep up the good work. Cheers, Lee. I think when Fred and I were first talking about James Webb, we talked about the fact that they had to get this absolutely right first go because there was no going back if they made a mistake. So that may well help answer the question from Lee, but your thoughts, Jonti?
There aren't any plans at the minute for JWST Mark II, Mark III. It's interesting when you go back to Hubble that the US military has spare Hubbles lying around. So there's great observatory coming online in a few years' time when it gets launched. Nancy Grace Roman telescope, I think it is, that has its origin in the fact that Hubble Space Telescopes are now old technology for the military. So NASA got approached, apparently, and told, oh, by the way, we've got 3 or 4 spare Hubbles lying around. Could you use them? And the ones that the military were using obviously point in a different direction because they look down rather than looking up. I don't think that's the same story with JWST. And part of the issue here as well is the development time. JWST famously launched about 20 years after it was initially scheduled to. And the first discussions, the first planning for JWST was actually in the 1980s. And it took until 2021 for it to get launched. That's really challenging. And there is nothing in the pipeline to do it now. The idea of having the production line is something that's become relevant for smaller telescopes. We at UniSQ have this fabulous observatory, Mount Kent Observatory, where we've got a dedicated facility for finding and characterizing planets under the stars. And we're able to do that on a university scale budget with our collaborators, because for smaller telescopes, there are now companies who produce these things on a production line. And we're having essentially the Model T Ford revolution in telescopes, where for small telescopes, people, and by small telescopes here, I'm talking telescopes with mirrors that are 70 centimeters or a meter across. So they're still a lot bigger than your typical backyard scope, but they're small compared to JWST or compared to the Vera Rubin Observatory, things like that.
Yeah.
And there is sufficient demand from the military, from commercial interests, from astronomers, and from amateur astronomers that it's now sufficiently profitable for companies to do these things on a production line. And what that's led to is a drop in the cost of these telescopes of an order of magnitude, which lets us build these bespoke observatories that are tasked with a single task to do a single thing. The problem is that production line thing is okay for telescopes that are 70 centimeters or a meter across. It's not telescopes at the cutting edge of the biggest in the world, the most complex in the world. These are relatively simple telescopes. There is no motivation, as far as I can tell. It's not a good financial thing to say, we're going to build a production line for JWSTs, because there's just not the market for them. The cost is so high, the use case is so small. I'd love there to be 9 out there, but I would lay odds that if there were 9 JWSTs, they would still be oversubscribed by 9 to 1, because there's just so much science that we want to get done. The focus is on the next generation of telescopes. There's the Vera Rubin Observatory coming online in the next year or two that'll see first light. That will revolutionize astronomy. I'm really excited about that. And that's ground-based. But that's an 8.3 meter diameter primary mirror, but a incredibly, incredibly fast photographic lens. So it's like having a really fast lens on your camera, but it being 8.3 meters across. That will let people survey the entire sky once a week, down to magnitude 20, which is about 1 billion times fainter than the human eye can see, every single week. And that's predicted to increase the number of objects we know in the solar system by a factor of 10 to 100 times within a year, to do similar things for the rest of astronomy. And things like that, things like the James Webb, which are really at the cutting edge of what we can do, tend to be one-offs because they're incredibly expensive. They require huge amounts of technology innovation to make happen. But they're also such an incredibly long lead time that by the time it's up there, people are planning the next big things.
Yeah.
And we're talking for space observatories about telescopes that won't launch until the late 2030s, early 2040s now. Nothing that I'm aware of is a direct analog for James Webb. It's probably worth having an aside here. I'd like to talk about this. You sometimes get people saying, why do we spend so much money on this? Why do the US governments continue to give billions to NASA? And shouldn't we spend that money on things like curing cancer? You know,
yes, really. Got your question semi-regularly.
And for me, what we as scientists always overlook is the fact that the motivations of governments to fund these things are not really the science. We always, when we get asked that question, say, but it's awesome and we want to learn stuff and we're so passionate. And that's a really valid answer if you share that passion. But if you don't, it's meaningless. What's actually going on with NASA and with other governments around the world that are pumping huge amounts of money into this is that they're aware of the return that they'll get on their investment. To build James Webb was ridiculously expensive. I think it's approaching $10 billion US dollars. That's billion with a B again. That's a lot for a government to invest, especially when you think, yeah, should we be investing in curing cancer? But to do that, you're looking at solving technology problems that have never been solved, building cameras to make measurements with a precision that's never been achieved. And that drives a huge amount of technological innovation. For the government funding NASA, the great majority of the people aren't at all interested in the science. But what they're aware of is that historically, since it formed without fail year on year, NASA has had return on investment of at least 10 to 1. So for every dollar that is invested, the return to the economy is more than $10. And there is no other business that I'm aware of that has that return on investment. So commercially, it makes a lot of sense. But also, for things like curing cancer, if you're a doctor who wants to cure cancer and you want to be able to study the human body, you're going to need better cameras, better detection tools, better software. But you're a doctor, you're saving lives. You can't say, I'm going to let my patients die because I'm going to go spend 5 years developing a new tool. That's not going to happen. But the tools that are developed for these astronomical things, for instruments, for facilities, for space observatories, then find use in other areas. I've got, my pocket-based, fruit-based device, my phone. Other brands are obviously available. Has a camera in it that when you take photos, they're awesome, and all the phone brands are like this. But the camera itself's terrible. You look at the phone side on, and you've got a tiny little light path to a sensor with mass-produced lenses. The images that these phones make are actually absolutely god-awful. They're terrible images because the optics is terrible, because it's cheap, reproducible, very small. But they're god-awful in a very predictable way. All the optics have the same flaws from one phone to the next, which means in the camera software, all of those flaws can be reverse managed out. So you go from a blurry kind of, hall of mirrors type experience to a beautiful image because it's reproducibly bad. The detector in that phone, the software that's used for that image processing, all of that stuff that we take so for granted in our pocket has come from astronomy research, from the image processing and the imaging that's done by astronomers. And that's really why governments invest in this. For you and I and for the bulk of the audience, we're just in it for the research and the excitement of the discoveries. But for the people in power, they see the benefits that this brings that are clearly very different to the scientific outcomes, and that's why it gets funded. And when you're passionate about something, when you care, you don't think about that narrative. You just talk about the excitement and the wonder, which is preaching to the converted. But the skeptical person down the pub who wants to know where their tax dollars are going in a time when we've got a cost of living crisis, telling them about the wonder of science isn't going to win them over.
No.
Telling them about the other benefits, they'll understand. And I think it's really important to have those discussions, even if they're not the wonder that we all want to espouse. And it's good to have the reality of the other benefits as well.
Indeed. Yeah, well said. There you go, Lee. Probably not a James Webb Space Telescope 2 and 3, but I can tell you for sure, and Jonti hinted at this, over the next, between now and 2051 and beyond, there are plans to launch 22, 23 space telescopes. So they won't be James Webb. They'll all have different tasks. One of them will be studying gravitational waves. Others will be looking at gamma rays. The list goes on. But they're... Sorry?
Oh, there's exoplanets as well in there. There's all... Yes. And James Webb is a very multi-use tool, so it's good for everything. But you quite often get more mileage by making a cheaper tool that's good for one thing.
Yeah.
And a lot of these facilities are designed for a specific task.
Yeah. So in the coming few decades, 22, 23 at least, space telescopes are going to be launched. So it's not something that's stopped at James Webb by any means.
What I might do quickly on that topic is actually hop off one soapbox and climb up on another one.
Okay.
Which is the challenge involved in this. So you say, next 20 years, we're talking about maybe another 20 or 30 space telescopes to be launched, and we might get a bit more than that in actuality. One of the things Starlink proponents will often argue to astronomers when astronomers say, oh no, the sky's getting ruined and it's going to be damaging for ground-based optical observatories. It's just, ground-based observatories are obsolete anyway. Elon Musk can just launch all your telescopes to space and that's the problem solved. And it just doesn't work that way. I mean, I did some reading around when this debate kicked up again. There are more than 10,000 professional ground-based astronomical telescopes on Earth that are doing research that are all oversubscribed. The smallest of them are things like up at our observatory at Mount Kent. At Mount Kent, we've got more than a dozen telescopes all actively on sky every night doing really good research. And the smallest of them are our 70-centimeter telescopes. We're involved in a space mission called Twinkle. Twinkle is looking at putting a 70-centimeter telescope in orbit to do infrared observing. And it's kind of crowdsourcing it and building it off the shelf. It's a new model of telescopes, which makes it hugely cheaper. That will cost $70 million. Our 70-centimeter telescope on the ground cost us $250,000. There is just not the money to reproduce what we've got on the ground in space. There is also not the capacity to launch the really top-end stuff. The Vera Rubin Observatory is going to be an 8.3-meter mirror with a 5.3-meter secondary. Crazy huge thing. The biggest telescopes they're building at the minute have nearly 40-meter diameter mirrors. There's just no way you could launch them. Though, unfortunately, it's a bit specious to come back and say, we don't need to protect the night sky because you can just launch all the big telescopes to space. We can't afford to, unfortunately. So we need the ground-based stuff as well, and the ground-based stuff does amazing work.
Indeed it does, yes. Very well said again. And Lee, thanks for the question. It certainly sparked Jonti into action. Thanks for getting in touch with us. Lee, Lawrence, Rennie and Christian, who made up our panel today with our text questions. Thanks as always to you. And if you've got questions for us, don't forget to send them in via our website, because that's the best way to get them through to us, whether they're text or audio. We take them all. If you want to put a question on a paper airplane and just throw it, it might get to us. You never know. And Jonti, as always, thanks so much. We'll catch up with you again next time.
Looking forward to it. Thanks for having me, and, clear skies to everyone.
Jonti Horner, Professor of Astrophysics, sitting in for Fred on Space Nuts at the moment. And thanks to Hugh in the studio, although he couldn't be with us today because he's actually waiting in line for his turn to use the James Webb Space Telescope. And from me, Andrew Dunkley, thanks for your company. We'll catch you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.